Welcome to EDU World Space.
Here we're going to look at the time-averaged potential energy of two objects in orbit about each other, whether they're a planet going around the sun or two stars in a binary system. So we are going to use a simple math weighted average as shown, that the average of any function of any variable is the integral of that function over a specific period or specific limits divided by that interval. And usually you do this if you're talking about something that's periodic, but it's actually the same formula as finding the center of mass of an object with a spatial average. Anyway, we are out to look for the time-averaged potential energy, which is given for gravity as minus big G times the product of the two masses in the system divided by their R, their separation, their mutual separation. And really the stuff on top of that is a constant. So that will pull out. That will pull out of the integral. And of course, the period is the period of the orbit, P period. And so we have to find the time averaged value over one period of 1 over R. Okay, and how do you do that? Well, R is typically given as a function of theta. So the differential equation with the time in it is rather difficult to deal with. Let's put it that way. So what we have is R as a function of theta. And the game here is, how do we turn this into a function of time? Well, that is a good question. And the secret is Kepler's second law. Hey. Okay, so to get R as a function of time, we will use Kepler's second law. And by the way, this is how you can develop a program to determine R as a function of time with calculation over a full orbit. You can get R as a function of time. So let's see. What Kepler's second law says is that the time rate of change of the area swept out by an object in orbit, and we'll draw a better picture, but I'll just sketch it over here. So the sun is sitting, we'll make it easy. We'll put the sun at a focus, and we'll put a little planet going around the sun. And what we're told is that between any 2 points that the planet makes, the area that it sweeps out per unit time is a constant. So let's say in the upper A to B, it sweeps out a certain area, and then going from C to D, it sweeps out the same area. Then we know that those time intervals are the same if the areas are the same. And we can then relate this to the entire area of the ellipse, pi AB. That's the entire ellipse divided by the entire period of the orbit. Okay, so that's one thing. That's a constant that we can relate to orbital parameters. The second thing to realize is that if you blew up a very tiny infinitesimal slice, okay, where the R is basically staying pretty much the same from one point to another, and this is not going to be very exact, but you'll get the idea. but shrink it down to a wedge of almost nothing with an infinitesimal d theta, then the area of that wedge is basically 1/2 base, which is r, times the height, which is the arc length, r theta, d theta, actually. And that's a differential area. Okay, shrink it down to nothing, and this becomes a very good approximation. Well, becomes perfect. All right, and then we can simply say that the area by dt then is equal to 1/2 r squared d theta by dt. Okay, so basically we can relate, and yeah, this has to equal the constant that we've already figured out, pi ab over the period. So we can relate r squared delta theta to a delta time. And this becomes a perfect thing if your d time is small enough, if your d theta is small enough, etc. Okay, so let's see how we do this in the integral. So what we have is a d theta, a dt in the integral, which we want to turn into a d theta. So we're going to do the mathematical trick of just cross multiplying by dt and getting the other stuff with the d theta. And so we have 1/2 r squared d theta, and then the inverse of all that constant stuff, pi ab in the denominator, period on top, is equal to dt. All right, and so we can use this up in our integral, and lo and behold, we get an integral in theta instead of in time. And because we're going over the full cycle, our limits on our integral will become 0 to 2 pi. Okay, so now u with dt going to d theta, we can use our r as a function of theta. Okay, and then we've got all this 1/2 pi in the denominator, ab. And then inside the integral, we've got r squared over r d theta from 0 to 2 pi. And life will get good. So notice that one of the r's disappears, and we now have r integrated in the numerator. There's some other stuff that disappears. The period disappears. So we can clean this up a little bit. Minus g, product of the masses. We still have 2 pi ab downstairs. You'll see what happens to those. And now we can integrate the r, as a function of theta. Okay. Which is the nice little elliptical conic section in polar coordinates. Okay. Which sounds so innocuous. Yeah. And there's some constants that come out. Orbital parameters. And we're left with this nasty looking beast, which doesn't look nasty, but it actually is nasty. And the mathematicians tell us that there is a closed form integral of that quantity. Going through that integral is not an easy piece of pie. You have to use something either called the Weierstrass substitution or the residue theorem on the complex plane. And that is sort of an advanced math topic that most people don't get to in their first 3 semesters of calculus. So it is best to take people's word that this integral is 2 pi over the square root of 1 minus e squared. And there's probably some very interesting math that goes into that. So notice what will happen is now when we're done with that integral, some more things will cancel. And the a cancels as well. I forgot to do that. And so we're finally left with something in terms of the semi-minor axis. And here's the real fun is you might not have remembered this, but the ratio of the semi-major to the semi-minor is 1 minus the eccentricity squared to the 1/2. And that does come from Pythagorean theorem and definition of the eccentricity, but we won't get into that geometry. So A is essentially B divided by that square root quantity. And we see that that is exactly what we have in there. So the time averaged potential energy is simply the potential energy the two objects, the two masses, have when they are separated by the semi-major axis.